All right, so now that we have our basic idea of what our neural network is going to look like architecture-wise, let's go ahead and implement that. So in PyTorch, you always put your neural network kind of modules into a class. We'll just call it, we can call it neural network, keep it simple. If you had a more specific name, like you were trying out a new model, you could call it that, but we're keeping it simple. It's just like a vanilla neural network, so we'll just call it neural network. And all of these inherit, so in Python, when you have a class that inherits from another class, you pass the parent class into the parentheses right after the name of your class, and we'll be inheriting from nn.Module, and we actually have to import nn first. This is the neural network module, so from torch import nn. And if you're curious about what exactly this nn.Module is, you can look up nn.Module. And here you can see this is the base class for all neural network modules. And essentially what's going to happen is we're going to have these two functions, init and forward. And this is just an example, so you're not going to always do this here. But the idea is the same, that you're going to inherit from nn.Module, define an initializer, or like a constructor, if you remember from like C++, and forward, which is when you go through the network. So let's go ahead and implement this. So our class is going to have, let's first just do our init function. And these are double underscores. So init for any Python class is when you make a object of that class, this always runs, and it'll always set up things like the variables for your instance, things like that. So what we'll do is we'll actually first call super, this is just kind of boilerplate, you'll always do this, neural network self.init. And once you do that, then you can start setting up what your actual architecture looks like. So just to keep it nice and clean, I can add some comments. So what we'll do is a neural network with 4 layers. The first layer we have is an input layer with 784 neurons representing the image, and then we'll have 2 hidden layers with 512 neurons each, and then we will have our like output layer with 10 neurons representing the label. Cool, so the first thing we need to do is, actually what we need to realize is that the data that we printed out here is 784 values, but the problem is it's not all in one dimension. We have a 2D array because our image was 2-dimensional. We have this 2D array. So the very first thing we'd want to do actually is just flatten that data. So we'll do self.flatten. So this is like our, I guess it's like before our input layer, it's our flattening layer. It'll go and flatten the input. So neural network.flatten. Again, if you're curious about what these methods are doing, you can always just search them, nn flatten, PyTorch, and you'll see here it takes in the input and it flattens them into a tensor, and what we can do is exactly that. And then once we have that, then this kind of like pre-processes our input for us, and once we do that, we will self.first layer. So this is really going from our input layer to our first hidden layer. So the way we can think of that is we're going to do 2 operations. So if you remember from the 3 blue 1 brown video, you want to do the weighted sum from the previous layer to the current layer. So we're going to basically have a linear kind of combination of the previous layer into each neuron for our current layer, into our first hidden layer. But then we also apply some nonlinearity. And in the example in the video that the 3 blue 1 brown video had was we want to squeeze the number into a range of 0 to 1, or it could be a different range. So some of the activation functions we have, so we could look at the sigmoid function. This squeezes the result into, let's go to the Wikipedia article. This squeezes the results into the range 0 to 1. There's another one called tan h. This is another popular activation function. Let's look it up here, actually. Tan h activation function. This is very similar to the sigmoid function. This is actually a nice comparison between the two, except it ranges from -1 to 1, whereas sigmoid goes from 0 to 1, and the other one, there's a lot of activation functions, but the one that we'll actually use is called ReLU, which it basically takes your input number, and if it's negative, it just turns it into 0. So there's a lot of like kind of different choices you have for activation functions, the thing that you apply after doing your linear combination. And the more in-depth you go, you'll kind of learn which ones are better for which scenarios. But for now, just kind of realize you can pick any of them. We'll just stick with ReLU, but you could pick any of them, and it'd be cool to experiment with a couple of them and see which one works the best. But we're going to be doing two operations, so we'll do this in nn.sequential, because we have a sequence of things we want to do. The first thing we'll do is nn.linear, so we're going to do a linear combination from the input layer to the first hidden layer, and the parameters that linear takes are the dimensions that you're going from and the dimensions you're going to. So for our input layer, we have 784 neurons to start with, and that, again, was 28 by 28, so I'll just write it like that so it's really clear. And we're going to the hidden dimension size, which is 512. I'm not a big fan of like hard coding numbers in here, because if you want to swap them out, and like, you know, this could get much more complex if you had more code. So it's nice to be able to like just have your class variables up here so you can easily edit them. So this input dimensions, 28 by 28, so again, this is the image size, and our hidden dimension will be 512. So instead here, let me call self.input dimension and self.hidden dimension. So we'll do the linear combination from the previous layer to the first hidden layer, and then we'll apply our nonlinearity. And in our case, we're doing nn.ReLU. You could do the other ones. You could do sigmoid, tanh, any other activation function, but we'll stick with ReLU for now. And then that brought us to our first layer. So now we want to go to our second layer. It's going to be pretty similar. We're doing the same process of doing a linear combination and then applying a nonlinearity. So we're going to do another nn.sequential. We're doing two things. First, we're going to do the linear, but the difference here is that we're no longer mapping from the input size to the hidden dimension size. We're already at the first layer, so we're already at hidden dimension size. And then because each of our hidden layers has 512 neurons, we're going to map from that size to the same size. The first layer mapping to the second layer, there's actually the same number of neurons, so we're going from the same 512 to the same 512. And again, we'll do our ReLU. And the very last step then is to go to our output layer, and that output layer is really just classifying the input, so I'm going to call it self.classifier, and that will be nn.linear. And it's mapping from the hidden dimension, which is the second hidden layer, to the output dimension. And actually, let me also do this as a class variable, and that will be 10, because we have 10 possibilities for like the article of clothing that we're mapping to. So this will be self.output dimension. And we could, if we wanted to, we could apply another nonlinearity here. If we want to like scale it down to 0 and 1, we could apply sigmoid, but we don't have to. We can, because you know, if it's a large value, it'll still be a large value when it's scaled down. So we'll just leave it as a single linear layer. But this is basically our neural network architecture. We have our kind of pre-processing step where we flatten the input from the 28 by 28 2D array into just 784 values kind of in a flat line. Then we map to our first hidden layer, which is 512 neurons, and we map to our second hidden layer, which is the same size, and then we map to the output layer, which is our classification step. It's really telling us which image type that we have. So this initialized the architecture, but then when you actually want to pass a piece of input through your neural network to get the prediction, you need this method called forward. And this will take in the input, and we'll just call it, x. And what this does is it passes the input x through the neural network to get its predicted output. And the reason I'm saying predicted output is because we don't know if it's like the correct one or not. That's what our labeled data is for, that we have the label to compare with, but we're getting our predicted output from the network itself. So the steps for this are actually pretty straightforward. We will take our input x and just pass it through each of these components, until it gets to the output of classifier. So the first step, we can say, like, let's say flattened x is what happens when we call self.flatten on the input. So take that 28 by 28 kind of 2D array, the 2D tensor, and turn it into a flattened tensor. That's just one dimensional. The next step would be passing it through self.first layer, and we can call that, let's call this like h1 for the output of the first hidden layer. You can really call these anything, it doesn't really matter too much. And then h2 would be, okay, we pass it through the first layer, let's pass it through the second layer. And here again, notice that we're not passing the same x, we're doing the change, and then we're passing that through here. So this was h1, now we're passing h1 to get h2, and now our output is self.classifier of the second hidden layer's output. You can call this anything, you can call it output, you can call it like z, you can call it whatever. I'm going to call it logits because it's a prediction from a classifier, so it's like a probability distribution over which neuron's most likely to be the label. But again, this is just a terminology that, you know, it's nice to learn, so you can be exposed to this. So it's just logits, and then we'll return those logits. And again, this is just the output from the last layer. And you don't really have to, like, you know, rename it every time. Like, I could also just call this x, and it'll overwrite it. So it doesn't really matter, again, the naming too much. It's just you're going through your neural network architecture in order to get your output. And that is pretty much it for just setting up your basic architecture. You'll realize now that we need some kind of way to actually train the network, because right now all we have is the architecture, but no way to train it. So what we'll do next time is go through the process of how to train the network, and actually run some examples and see, is it learning properly?